Hello, everyone, here in the room and virtually at your home. My name is Csaba Fitzel, and I will talk about macOS vulnerabilities hiding in plain sight. A couple of words about myself. I'm currently working for Offensive Security as a content developer, and I'm the lead content developer there for our macOS control bypassers training. I used to do macOS bug hunting in my free time as a hobby. Before that, I was a blue and red teamer for about 8 years. I'm married, have 2 kids, and I really like to do trail running, hiking in my free time. So what I will talk about today, I will start with a short introduction about the whole concept behind this talk, and then covering 3 different vulnerabilities I found. The first is a privilege escalation on macOS using the system preferences daemon. The second one is a TCC privacy bypass, and the last one is a Sandbox escape. And for each of the CV or for each of the vulnerabilities, I will cover some technical background of the given process or framework. Then I will talk about the original vulnerability and the exploit that led me to find the new one, and then obviously also about the new one. So the whole concept behind this talk is we often say that someone can see the forest for the trees. And that's often because we are so focused on something that we don't notice something behind, or we just miss something. And personally, I think that's a human nature, so this is just how we work. And also, I think nowadays there are so many articles, like even technical articles, information that we want to consume, that we simply have no time to actually deep dive or many times read in depth many of those articles. So, but sometimes I happen to read some articles again and again, maybe because it was so interesting, maybe because I forgot what was inside, or I need to look up some information again and again. Obviously, we cannot remember everything. So this is how it happened, that there were a couple of vulnerabilities that I always returned to and read them again and again for some reason. And eventually, I found some new vulnerabilities and actually hid them inside the article, except one, which is a little outlier, but that's the whole idea. So let's start with the first one, which is CV 2021-1815, which is a macOS local privilege escalation in preferences. So what is CF-prefsd? This is, I think it stands for the core foundation preferences daemon. CF is core foundation. That is where the preferences API lives. And basically this process is responsible for setting application preferences on the system. There are 2 of them. One is running as a user, and one is running as root for system-wide preferences. And basically, you can interact with this daemon through the preferences API. So the whole settings is hidden. But behind the scenes, the preferences API uses direct XPC calls to talk with CF-prefsd. XPC is an inter-process communication unique to macOS or iOS, basically all the Apple operating systems. So the original vulnerability was part of the Pwn to Own 2020 macOS exploit chain, where the team there basically exploited macOS from Safari to kernel through a 6-step exploit chain. I think that was a really neat chain with lots of great ideas. And one of the steps was to get root privileges from admin. And this is the original vulnerable code, what we see on the screen. Basically, what happened there, the preferences daemon allowed someone to change the ownership of an arbitrary directory to the user. So what they did in the original exploit, it was a race condition exploit, so they raised it with a symlink. And they eventually changed the ownership of the etc/pem.d directory. The pemd directory is the pluggable authentication modules directory where all the PEM configuration lives. And after the permission was changed, they basically changed the sudo config file so they could get root without a password. And Apple fixed this, and the team, the Pwn2Own team, reversed the fix, and it was presented at Black Hat, I think 2019. And this is the reversed fix code. And this is good, so it basically ensures that symlinks are not allowed anymore, or at least they are not followed. Thus, exploitation wasn't possible anymore. So it all looked nice and clean. However, at one point it hit me that it's still not right, because in this code we still have the mkdir@, function, which is basically creating a directory on the system, and that is run unconditionally. Okay, so that means that we can create a directory somewhere, and basically after that the next checks will be passed again for any regular call, and then the ownership of the newly created directory will be set to the user. So what that means is we could create a new directory somewhere on the system with root privileges, so it can be set anywhere and then changed to the user. So this is a privilege escalation scenario, but it wasn't obvious to actually exploit it because we can only create a directory somewhere. So how we can turn it to code execution? On macOS, we have periodic scripts which are originated from BSD. These are maintenance scripts run on a daily, weekly, monthly basis. They clean like the temp folder or other files and do some maintenance stuff. And these scripts has a configuration file, and this configuration file defines a local periodic script location where the user can drop their own scripts that he would like to run. Now this location, this usr/local/etc/periodic, doesn't exist by default. So what we can do is use this vulnerability, create this directory as the user again, and drop our script there. And since these periodic scripts are executed as root, what we drop there, it will be executed as root. The only problem with this method that it's a bit slow because those scripts are invoked daily only, so that's the shortest time frame we can go. It can take up to a day to get root, but if you are on a slow engagement, that's probably not a big issue. Also, this will not work beyond Big Sur 11.5 because Apple made another patch that time. Now the periodic scripts, if the periodic scripts is owned by the user, it will not be executed as root, but as the user. So this exploitation method no longer works on like Monterey. So here is a short video of this. So we can see that the USR local directory is empty. We run our exploit. And now we can see that the directory is created and we will have our script there. And now I basically simulate the execution of the daily periodic scripts. And basically we will see terminal popping up as root. We could wait for the periodic scripts, but then it would be a really long video. So yeah, we got a root. So I kind of think about how we could exploit it through another way. And I came up with another, again, unperfect way, but this could be another method to exploit this vulnerability. So on macOS, there is this sysdiagnose utility, which typically runs as root. and it tries to execute many binaries from the USR local bin directory, which again doesn't exist by default. So some of these have been remediated now, but still there might be some out there that we can invoke. So basically what we can do in our exploit, create this USR local bin directory, drop one of the binaries there, and hopefully it will be invoked. Although sysdiagnose contains all these references, it doesn't always call each of these. But again, it's not perfect because it depends on the user triggering the sysdiagnose utility. So it can be either done manually, so the user is typing in sysdiagnose and enters his password to run as root. The other way is to launch Feedback Assistant and create a new case. And then Feedback Assistant will automatically invoke sysdiagnose to attach the result to the new feedback ticket. Now, I actually looked into this, how Feedback Assistant, which runs as the user, can invoke sysdiagnose, which runs as root. And it turned out that Feedback Assistant had some private entitlements that allowed it to basically invoke sysdiagnose and run it as root. So unfortunately, we cannot achieve the same if we are not Feedback Assistant. The third way to invoke sysdiagnose is to use this keyboard shortcut, which is Command Option Shift Control period at one time, and then sysdiagnose will start. But again, if we are a malware or pen tester, we cannot simulate keyboard shortcuts or keyboard entries. So that was the first one. The next one is a TCC bypass. This was a shared finding with Wojciech Regula, who is a guy from Poland I often work with. So what is TCC? TCC is a security feature on macOS, which is responsible for protecting all of the privacy-related resources on the computer. So like microphone, camera, your photos, your contacts, your documents. The list is quite long. It's basically whatever Apple considered private. It will be protected. It mainly works by two SQLite databases. One is located in the system library application support com apple tcc/tccdb. And the other one is it's the same location, but in the user home folder. So some of the settings, like microphone and camera, is set on the user home folder. Some of the settings, like full disk access, is controlled through the system-wide database. So that's just a really short intro to TCC. If you want to know more about it, I defer to our talk with Wojciech from last year, Black Hat, about the 20+ ways to bypass your macOS privacy mechanism. So what happened here? Last year, the XC set malware used the TCC O-Day, which is, I think, highly unusual for a macOS malware to use any O-Day. But they did one. And basically what happened there is that the malware enumerated the applications on the system, and let's say they found Zoom. Now, Zoom is a video conferencing application, and it very likely has microphone and camera access granted by the user. Otherwise, it couldn't work, and then there is no point to have Zoom on your system. So it likely has those permissions. And then the malware created a new application bundle, which was an Apple script-based application, and copied that application inside the Zoom application bundle macOS folder. In the macOS folder, usually you have the main executable of the application. So they simply copied the new application bundle into this location and started it. And what happened that time, macOS was confused, and it thought that it's actually Zoom that is running and not this avatar application, and it basically inherited Zoom's privacy permissions, so it could access camera and microphone. So basically, macOS wrongly identified the bundle, which would be already a hint here, but this was fixed. And then later on, again last year, Mickey Jean from Trend Micro played more with this vulnerability and found the bypass. The TCC database contains the bundle ID, and basically just by creating a new application with the same bundle ID as our target, so let's keep Zoom as our target. So he created a fake application, put the same bundle ID as Zoom, and when he executed the fake application, the system was confused again to think that it's Zoom that is running, and it inherited Zoom privacy permission. And again, the issue was that all the code signing verification and everything was done on the main Zoom US .app application and not on the fake application, which is a problem. And this was the point where it hit me that there is a fundamental issue here with TCC, which enabled both vulnerabilities, and it's the fact that macOS didn't verify the code signing properties of the running process, but it verified something on the disk. Now, the TCC database does contain the code signing requirements for the application, so it properly identifies the application. Now, obviously, when we start our fake application, it will not have the same signature as Zoom in this case. So if they were verifying the process, it could have been identified that, hey, it's not Zoom what is running, but something else. And this was really shocking a bit, because on macOS, you never verify code signature on disk if you have a process running. Because what you can do on macOS, once the process is started and running, you can basically delete that application or delete that binary, and it will keep running until it's shut down. Unlike on Windows, where you cannot modify or delete the binary of the application. So usually every time on macOS, because of this, the code signature is verified in memory. Well, except Gatekeeper when the process is not even running. Of course, then we have no choice. Also the same issue with XPC and Mac message or Mac connection verification. When we try to verify the connecting client, we should always use verify the connecting process signature based on its audit token. So even like the process ID is not considered secure on macOS for this. And like on disk, on XPC or Mac verification, it doesn't really come up at all as a verification step. Although I saw vendors being very creative and doing this, like Adobe. It's fixed now, but yeah, so you should use audit token. And based on the audit token, verify the process. Also, MFI checks in-memory integrity checks, again, in memory and not on the disk. So what we could do is really simple. Make a fake application with the same bundle ID as our target. So let's stay with Zoom. I have no issues with Zoom. It's a great app. We just use it as an example. We start our application. Then we take Zoom and copy over our fake application. Then we initiate some actions that require privacy permissions, like recording camera, microphone, or accessing various locations. And it will be permitted. And we bypass TCC because the bundle on the disk is verified. Or Wojciech made an alteration to this. So we make a fake app and embed it in our donor app with the same team ID, start the app. Again, copy over the donor app over the app, the fake application, and initiate the action. And again, we bypass TCC. So here's a demo of this. So we can see that we have Zoom on the system. Zoom has audio input, which is microphone and camera access. I'm opening system preferences and showing that indeed Zoom is granted these permissions by the user and nothing else, basically. And then I have the other fake Zoom application, which has no rights at all. Now I start the fake Zoom application, and we can see that the size of the application is growing, and this is because at this stage I'm copying over the original Zoom application over the fake one, and then we can see a new MOV file is showing up. This is like a 10-second recording with my camera. And it's done, and yay, I recorded myself. So this has been fixed now, luckily. So based on the TCC daemon logs, we can actually confirm that finally macOS, the TCC process on macOS uses the dynamic code signature of the process to verify code signature. So if it's done. And the last one is a Sandbox escape using the disk arbitration service. It's been fixed, so no O days, but there was no CV assigned yet, so that's why all the X is. So what is disk arbitration? It's basically a service for managing disk mounting and mounting. It can also notify us if there is a new mounting happening, and we can even set handlers on our own programs that we maybe permit or deny specific mount operations. So that's what it does. It has an XPC service, but under the hood, it will call the mount and unmount regular system calls. So why disk arbitration is the daemon, why we like it, why is it good for us as pen testers or security researcher, bug hunters? So first, it runs as root, which is nice. It runs on Sandbox, which is also nice. It has an XPC service, which is accessible from the application Sandbox. This is part of the application Sandbox profile, and we can see that the disk arbitration service is permitted at the bottom. So basically, any regular Sandbox application can access this service, and it's also open source. So it's like the dream combination at this stage. So again, first the original exploit from 2017. It was also done in one of the Pwn2Own contests by the Fernhex team. It was again part of an exploit chain, and this was also a privilege escalation. So what disk arbitration does to prevent abuse, because it runs as root, if someone calls this service, it will check if the calling process has permissions to mount over a specific directory or not. Obviously, if this check wasn't there, then someone could mount anywhere and escalate privileges trivially. So what it did, it took the path given to the mount location, resolved it, checked that can the calling process mount there or not, and if yes, then it kind of proceeded, did something, and then it resolved the path again. Which was a problem because there was a time of check, time of use bug because of these two resolutions. And basically, once the check is done, we can do something with that path using symlinks and point it to somewhere else and basically mount somewhere else on the system, not on the location where the check was done. So this could be exploited with a race condition, like a race. And what the team did at 2017. They mounted the EFI partition, which is admin writable, and they mounted it over the cron tabs directory and created a new cron job there and escalated admin to root on macOS. Now, the new one, so this is a bit outlier from the previous two. This doesn't come directly from the article, but when I opened the source code of disk arbitration, the new one, I realized that the same verification step, there is a new one for Sandbox checking, because Sandbox is disk arbitration is reachable from the Sandbox. Disk arbitration has to also ensure that the Sandbox application has rights to mount on the target location. So it runs a Sandbox check by audit token, which is a system call to the Sandbox driver. And it will check if mounting is permitted for that process or not. Now, let's see how the check was done on the old vulnerability for the mount point location and the new vulnerability for the Sandbox. So we had the path retrieved the same way. Then we have the same if statement. And then the same path variable is used on the old version. It was used for the user ID permission check. And now the same way it's being used for the Sandbox check. So it looked like the same logic issue is there, but now not for privilege escalation, but for a Sandbox, potential Sandbox escape. So what I did, as it's a race condition, and if I were directly going to exploit it and it's not successful, I wouldn't know if it's because my exploit is wrong for any reason or it's simply not exploitable. So I created a Sandbox profile which simply denied mounting over the private temp disk directory. And launched a shell with this profile and then tried to do two mountings, one for disk and then disk 2. And the profile was working properly, so like temp disk wasn't allowed while the other one was allowed. So I launched a debugger and attached it to disk arbitration D. For this, we need to disable SIP on the system so we can debug disk arbitration. And set a breakpoint on the Sandbox check by audit token. And then I run the mounting again. So I wanted now to mount over temp/disk2 again. And then we hit the breakpoint. I set finish on the check. And I'm not sure how well it's seen, but basically it returned 0, which means, yes, you can go ahead, it's permitted. Of course, because I want to mount over temp/disk2. But what I did at this stage, I'm still holding the service. I removed the disk2 folder and created a new symlink as disk2 pointing to /temp/disk, which is the original location, which wasn't allowed by the Sandbox profile. I continued the process, and voila, I could mount over that location. So that at least confirmed that, yes, the bug is there, so it's exploitable. Now I need to really exploit it. And it turned out to be not trivial. Because the first question was, okay, what do I mount? EFI partition is really out of question. First, because disk arbitration now has a specific check for the EFI partition. That's what we see there. So that long GUID is for the EFI partition. But even if I could mount it, I mean, I cannot reach that location from the Sandbox. So okay, let's mount a custom DMG file. A DMG file is like a disk image on macOS. Okay, so I plan to mount a disk image, but the problem is that disk arbitration service doesn't work with disk images. It works with /dev devices. So how do I get a /dev device from my DMG, and that is what disk management daemon for. Disk management daemon can turn a DMG or map a DMG file into a dev device, but disk management daemon is not reachable from the sandbox. And it happened to me that, okay, I cannot reach disk management D, but what I can do is I can call the open system command on the DMG file, and then the system will automatically map the DMG file into a dev device and also mount it at the same time into the /volumes directory, which is nice because now I have a /dev device, but it's also mounted what I don't need at this point because I want disk management daemon to mount it for me. But I can use the disk management daemon to unmount the /volumes whatever name location, and the dev device remains in place. So that was nice because now I can mount something, an arbitrary file, create a dev device. So the last question was, okay, where do I mount to actually achieve code execution outside of the sandbox? And there might be multiple ways to do it. My idea was to mount over the home library preferences directory, where we have all the preferences file for all the applications that runs as the user. Now, the terminal has also a preferences file, and it has a preference that the command string, and we can put there any bash or shell command, and it will be executed when we launch terminal. So let's put it all together. We have our sandbox application. We drop a DMG file. We call open on the DMG file, so it will be mounted, and also the dev device is created. Then we unmount the mount point, but our dev device is still in place. And then we will start our race. So basically, we want to mount over the preferences directory. And once we want to mount over inside a container in a folder which is permitted, and we race it with a symlink. And eventually it will succeed. So eventually we will mount over the preferences directory, and once we manage to do that, we stop our race, and then we open terminal. We can do that from the sandbox. So from the sandbox, we can call the open command and launch an application. And once we started terminal, our code will be executed on sandbox, because I forgot to tell that terminal is not a sandbox application. So that's why it was the target. So here's another recorded demo of this. So I have the DA escape application, which is sandboxed. It has the COM Apple Security App Sandbox profile. And I list the currently mounted locations, so we can see that the preferences directory is not mounted over. And then I simply start the application. And at this point, it will start the race. We can also see that some mounting happening. It's finished. We launch terminal, and we mounted over the username library preferences. And now if I open the terminal profiles and go to the shell, now we can see that there is a run command set up. So basically, we achieved a sandbox escape through this mode. So conclusion to all of this, I think it's worth to read writeups carefully. I know we have no time to do it every time, but sometimes it's worth, and we can find hidden gems there. And it's worth revisiting all documentation, notes, articles, or code, or whatever, because again, we don't remember anything, and we might get new ideas by reading them again. Also, maybe when we originally read something, maybe we lacked some knowledge that we have now. So when we reread something, we read it with a different context or with a different knowledge set at that time. So it's worth to slow down sometimes. Thank you very much. I'm not sure if there are any questions.